All right, let's dive in. Today, we're basically going to be chemical detectives. Seriously, we're on a mission to solve a super colorful mystery that starts with what looks like just a few simple clear liquids, but it ends with us understanding some really fundamental chemistry. So you might want to grab your mental magnifying glass because our investigation is starting right now.
So here's the central puzzle. How is it possible that clear liquids can suddenly burst into all these different colors? You take one colorless solution, you add a couple drops of another clear liquid, and then boom, you get this vibrant color. How in the world does that happen? What's the secret? Well, that is exactly what we're here to figure out.
And here's our crime scene, so to speak. Check this out. Each of these test tubes started out with a different, perfectly clear salt solution. Then a universal indicator was added, and just look at the results. We've got a brilliant orange, a nice neutral green, and this cool blue-green. Now, I promise you, it's not magic. It is pure chemistry. And every single one of these colors, that's a clue. To crack this case, we first have to learn the secret code that's behind these colors. And that code, it's called pH. Yeah. It's this totally invisible property that these amazing colors are making visible for us. And here it is, the pH scale itself. It basically runs from 0 to 14. Just think of it like a spectrum. Anything that falls below a 7 is considered acidic. Right at 7, that's perfectly neutral. And anything above 7 is what we call basic or sometimes alkaline. This little scale right here is our decoder ring for this whole experiment.
Okay, so let's put our code into action. A universal indicator, which is what was used in our experiment, is specifically designed to change color depending on a solution's pH. So, if a solution has a pH less than 7, it's going to turn orange or red, telling us, hey, I'm acidic. But if the pH is greater than 7, it shifts over to blue or purple, signaling that it's basic. And what about the ones right in the middle? Yep, they turn green. This totally explains what we were seeing in those test tubes.
So, now we know the colors are all about whether something is acidic or basic. But what does that even mean? What makes something an acid or a base? And maybe more importantly, are they all the same? It's time to meet the main suspects in our little chemical mystery.
So, one of the clearest ways to think about this comes from something called the Bronsted-Lowry theory. And it really just boils down to protons, those little hydrogen ions. Acids are the givers, they are proton donors. And bases, they're the takers, they're proton acceptors. It's that simple give and take that really defines what they are at their core.
That's a fantastic question, right? If it's all just about donating or accepting protons, why do we get such different results in our experiments? And that question right there leads us to a really crucial new clue in our investigation, this idea of strength. We can actually see this strength in action. A great way to do it is to test how well a solution can conduct electricity. The more conductive it is, the more powerful it is. I mean, just look at the bulbs for hydrochloric acid and sodium hydroxide. They are glowing super brightly. Those are strong. But then look over at the bulbs for acetic acid and ammonia. They're pretty dim, right? That tells us they're... Okay, so here's the absolute key takeaway. Strength has nothing to do with how concentrated something is. It is all about dissociation, which is just a fancy word for how completely a substance breaks apart into ions when you put it in water. Strong acids and bases, they go all in. They dissociate 100%. Every single molecule just breaks apart. But the weak ones, well, they're a bit more cautious. Only a tiny fraction of their molecules actually separate. And that difference, it's the key to this whole mystery. And here are some of our usual suspects. You could call them the heavy hitters of the chemistry world. On the left, you've got common strong acids like hydrochloric acid. And on the right, common strong bases like sodium hydroxide. Now, try to keep these guys in mind because their strength is exactly what's going to help us solve our mystery.
Okay, deep breath. We have all of our clues in hand. We've got the pH color code, we know what acids and bases are, and we've got this critical idea of strength. It is time. Let's put it all together and finally solve the mystery of our colorful test tubes.
So the final piece of this puzzle is a process called salt hydrolysis. Now, I know, that sounds super complicated, but I promise, the idea is actually pretty simple. It's just what happens when a salt, which remember is just the product of an acid-base reaction, dissolves in water and starts reacting with the water. And that reaction is what decides the final pH.
Let's look at our first test tube. It had sodium chloride, yep, just regular table salt. So where does it come from? It's formed from a strong acid, HCl, and a strong base, NaOH. It's like a perfect matchup between two heavyweights. They completely cancel each other out. The salt that's left over doesn't mess with the water's pH at all. So the solution is neutral, pH 7. And what's the color for neutral? Green. Case number 1, solved. All right, suspects number 2, ammonium chloride. This salt comes from a strong acid, HCl, but this time it's paired with a weak base, ammonia. So this isn't an even fight at all. The strong acid's influence totally dominates. When this salt dissolves, it actually makes the solution acidic, which drops the pH below 7. And our indicator sees that and immediately turns that bright, vivid orange. And just like that, clue number 2 is cracked. And now for our final piece of evidence, sodium acetate. This time, the roles are completely flipped. It's formed from a weak acid, acetic acid, and a strong base, sodium hydroxide. So who wins this time? The strong base, of course. Its character totally takes over, making the solution basic, with a pH well above 7. And that gives us that beautiful blue-green color. And with that, my friends, the case is officially closed. You know, solving a lab mystery is a lot of fun. But the real power of knowing all this is seeing how it applies way beyond the lab. This was never just about test tubes. It's about the world that's all around us, every single day. Now that you get the basic principles of acids, bases, and pH, you're going to have a totally new perspective. You'll start to realize that you're interacting with this stuff constantly, from your kitchen to your bathroom, and almost everything you touch and taste. So let's pull out that pH decoder ring one last time. But instead of looking at chemicals in a lab, let's look at things you probably use every single day. The exact same rules that we just uncovered apply to all of this stuff. I mean, really think about it for a second. That sharp, sour taste you get from a lemon, that's citric acid. That kind of bitter, slippery feeling of soap on your hands, that's a classic trait of a base. Your morning coffee, acidic. The baking soda in your pantry, basic. Even our own bodies are masters of pH. Pure water is neutral, and our blood has to maintain this incredibly delicate near-neutral balance just to keep us alive. It is, quite literally, everywhere. You know, there's a quote that just sums this all up perfectly. Everyday life is the most wonderful laboratory. We don't need some fancy lab with beakers and burners to see science happen. The same principles that turn those liquids all those different colors are at play in your own kitchen right now. Our daily world is just this constant, fascinating experiment. So we've cracked the secret of acids and bases, but honestly, this is just one of countless chemical codes that are shaping our reality every single moment. So the real question to leave you with is this: what other invisible chemistry is hiding in plain sight, just waiting to be figured out? Keep asking questions, and always, always stay curious.